In this video, we're going to go over the KutaSoftware Infinite Calculus free worksheet, evaluating limits, and this is at essential discontinuities. So discontinuities where the function value either approaches infinity or negative infinity. So in numbers 1 and 2, we're going to evaluate each limit. For number 1, we're looking at the limit of x plus 2 over x squared plus 5x plus 6 as x approaches negative 3, and that's from the right. So coming from the right side of our graph, we're going to continue on f of x as x approaches negative 3. Here's a removable discontinuity at negative 2, but we're seeing the limit as x approaches negative 3, and that is positive infinity. So as we approach negative 3 for x, f of x grows to an arbitrarily large number, which we write as infinity. Now if we were to find the limit as x approached negative 3 from the right, that would be negative infinity because it's reaching an arbitrarily large negative number. Let's continue on to number 2. In number 2, we have the limit as x approaches negative 4 of x squared over 4x plus 16. So coming from the right, or from the positive direction, f of x is approaching positive infinity. However, coming from the left, as x approaches negative 4, f of x approaches negative infinity. And because an arbitrarily large positive number is not equivalent to an arbitrarily large negative number, the limit from each side is not equivalent, therefore the limit does not exist. Because remember, in order for the limit to exist, as x approaches a from the right and as x approaches a from the left, that limit will be equivalent. But since this is not the case in number 2, the limit does not exist. Now, on to number 3. For 3 and 4, we're going to evaluate each limit. You may use the provided graph to sketch the function. And I'll go ahead and use a graphing calculator to help us draw each graph. So here's our graph, and I'll go ahead and find points to help us draw that curve. At negative 8, we're at positive 4. At negative 5, we're at positive 5. At negative 4, we're at positive 6. And at negative 3, we're at 9. So I'll graph each of those to help me get this curve. So again, that was negative 8, 4, negative 5, 5, negative 4, 6, and negative 3, 9. So that's one side of my function. Let's work on the other side. Well, it crosses over the point 0, 0. At positive 4 in the x, f of x is equal to 2. It never quite reaches 3 within this interval for f of x. And x is negative 1, f of x is negative 3. So again, that's negative 1, negative 3, 0, 0, and 4, 2. And I'll get one more point between 0 and 4 for my x values just to help get a more accurate curve, and we'll give the point 1, 1. Drawing this curve, you can see that I have two asymptotes. I have a vertical asymptote at x equals negative 2. And you may be asking, what is a vertical asymptote? A vertical asymptote is essentially a vertical line for an x value that, as the function approaches that value, its limit goes towards infinity or negative infinity. And for a horizontal asymptote, I have a horizontal asymptote at f of x equals 3. And a horizontal asymptote is similar to that of a vertical asymptote, except in the case of horizontal, as our function approaches that value, then x approaches either infinity or negative infinity. So looking back at what we're to find in number 3, we're to find the limit as x approaches negative 2 from the right. So coming from the right on our function, approaching negative 2 for x, our function is approaching negative infinity. Therefore, negative infinity is our answer in number 3. However, I want to show you a quick tip for figuring that out without graphing. So our function was 3x over x plus 2. Now notice, as we're approaching negative 2, whether from the right or left, 3x, that approaches negative 6. However, for our denominator x plus 2, if we were to enter in negative 2 for x, that would be 0, and we cannot divide by a 0. But on one side, for values approaching 0 from the left, or values approaching 0 from the right, we're either going to have positive numbers in our denominator, or we're going to have negative numbers in our denominator. In this case, coming from the right, we would have values such as 0, negative 1, all the way up until negative 2. So if we were to plug 0 in for x, 0 plus 2, that's a positive number. So we know that 3x approaches negative 6, and x plus 2 approaches 0. However, that denominator is positive as it approaches 0. So because this is positive as it's approaching 0, and our numerator approaches a negative number, a negative over a positive is a negative, and this number is growing smaller and smaller, and dividing by a smaller and smaller number will give us a larger and larger value overall. So that's why it's approaching negative infinity, because a negative over a positive is a negative, and that negative number is growing larger. So let's look at number 4. Thinking about number 4 the same way we ended with number 3, let's see what these values approach. So our numerator, x squared, that is going to be approaching negative 1 squared, which is a positive 1. So we have a positive in our numerator. And x plus 1, well, that's approaching 0, because negative 1 plus 1 will equal 0. So leading up to that, we're getting closer and closer to 0. So our denominator approaches 0. Now we need to figure out whether it's approaching 0 as a negative number or whether it's approaching 0 as positive numbers. Well, looking at our limit, we're coming from the right of negative 1. So entering in a value to the right of negative 1 would be a value that's greater than negative 1, such as 0. And 0 plus 1 is positive. Therefore, since it approaches 0 as a positive number, our limit is growing closer and closer to a positive infinity, because it's a positive numerator over a positive denominator. So positive infinity is our answer in number 4. So let's go ahead and graph, and I'll use a graphing calculator to help us do this. So we'll have x squared, and that's going to be all over x plus 1. And I'll adjust my scale so that it matches the scale on our worksheet. So now let's work on graphing this function, copying down a few points to help us with the curve. Right away, we can see we have negative 2, negative 4 for the left side. And that's the point at which it changes from increasing to decreasing. So it's increasing up until that point with a slight curve. However, looking at the graph, it never quite reaches negative 8 in the x, and the more points you plot, the more accurate your curve will be. So let's find another point on this line. At negative 4, we'll be at negative 5 1/3. So let's plot that point. Negative 4, negative 5 1/3. And then using the fact that we never quite reach negative 7 in the x before our graph goes off the chart, I'll connect those points. And at that, we begin to curve sharply down, and again are out of our interval before we even reach negative 1, which we know is a vertical asymptote. And it's a vertical asymptote because it will give us 0 in the denominator and from the left or right. As our function approaches into x, it goes towards positive infinity or negative infinity. So there's our vertical asymptote drawn with a dotted line, so you know that that is not technically part of the graph. Then for this right side, we have the point 0, 0 coming from that vertical asymptote. And then to the right of 0, when we're at 1 in the x, our function is equal to 1/2. When we're at 4 in the x, our function is approximately 3.2, and we'll finish out our curve from there. So 1, 1/2, 4, 3.2, and let's get one more point at 6. We're at about 5.1. So then I'll connect those points with a curved line. So there is our plotted graph and number 4, and let's double check our limit. As x approaches -1 from the right, our function does indeed grow towards positive infinity. Now let's move on to the second page. On the second page, we're still evaluating each limit, however, this time we're doing it without the graph. But remember the trick I taught you in that previous section. For number 5, we have the limit of 2x over x plus 3 as x approaches -3 from the left. So as x is approaching -3, our numerator is approaching 2 times -3, which is -6. However, our denominator is approaching 0. And that's approaching 0 from, now we just need to figure out whether those are positive numbers or negative numbers. So if we're coming from the left, we're going to be coming from a number less than 3. So let's enter in -4. -4 plus 3, that indeed equals a negative number. So we're approaching 0 from negative values. So now we have a -6 over a negative number that is approaching 0, and a negative over a negative is a positive. So we know that this limit is going to be positive infinity. On to number 6. Regardless of what we put in for x, the numerator is going to be 1. However, the denominator is going to be slowly approaching 0 because -2 squared minus 4 is 0, but we need to see that we're coming from the right. So coming from a number that's larger than -2. Because remember, coming from the right is coming from x greater than a, so we need to find an x value that's greater than -2. Let's put in 0. If we plugged in 0, 0 squared is 0, and 0 minus 4 is a negative number. So we're going to have 1 over a number that's approaching 0 from a negative value. So a positive over a negative is going to be a negative, and that's going to be negative infinity. Because whenever we have a number over a number that continually grows smaller and smaller, that's going to approach infinity. We just need to decide whether that's going to be a positive infinity or a negative infinity. In the case of number 6, it was negative. For number 7, we have the opposite, or negative 4x over x minus 3. So I'll put this negative with the numerator. So -4 times a positive 3 is going to be a -12. So our numerator is approaching -12 while our denominator is approaching 0. However, we have to figure out whether that's approaching 0 from negative or positive. So far we have a negative for the numerator, and because it's approaching 0, we know that it's going to be infinity. We just have to figure out the sign that goes with that infinity. So we're approaching 3 from the left, so a number or value that's smaller than 3. Let's plug in 2. 2 is less than 3, and 2 minus 3 is a -1. So we're approaching 0 from negative values, and a negative over a negative is a positive. So this is going to be positive infinity for the limit in number 7. And at any point, feel free to graph and double check. Now in number 8, we have the limit as x approaches 1. But note, we're not given whether it's approaching 1 from the right or left, and I can tell that x equals 1 is indeed a vertical asymptote. So let's see if approaching from the right is equivalent to the limit approaching from the left. Now, coming from the right or left doesn't matter. The numerator is approaching -3, bringing that negative into the numerator. In the denominator, though, coming from the right, or coming from values that are greater than 1, we will have 2 minus 1, which equals 1, and it's positive. So a negative over a positive is going to be negative. So as x approaches 1 from the right, our limit is -infinity. Let's see as it approaches 1 from the left. Again, the numerator is approaching -3, and the denominator is approaching 0. So as we're going to +1 from the left, I'll start with a number less than 1 and plug in and see. Let's try 0, because 0 is less than 1. We're coming from the left side. 0 minus 1 is negative. So because we have a negative over a negative, that's going to +infinity. And -infinity does not equal +infinity. So because the limit as x approaches 1 from the right does not equal the limit as x approaches 1 from the left, our limit does not exist. Moving on to number 9, it's a good rule of thumb to always simplify, especially when dealing with a polynomial over a polynomial. So simplifying x plus 2 over x squared plus x minus 2, we're going to factor this denominator. So we're going to have x plus 2 in the numerator, and in our denominator, what multiplies to give us -2 and adds to give us a +1. That's going to be +2 and -1. So we'll have x minus 1 times x plus 2. But wait, we can cancel out x plus 2 and x plus 2. So we have that the limit as x approaches -2 from the left, that's equivalent to 1 over x minus 1. But now we'd be able to use direct substitution or direct evaluation and solve, because now we can plug -2 into the denominator and solve. 1 over -2 minus 1 equals 1 over -3, or we can write that as -1/3. So the limit in number 9 is not infinity and it's not -infinity, it's -1/3. This was just a problem they threw into the worksheet to keep you thinking. So don't forget, if you can factor and cancel out terms, you might be able to use direct substitution to solve for your limit. But if we were to factor, cancel out terms, and still could not plug in that value, then it would have most likely been a vertical asymptote at -2, not just a removable discontinuity. That is the difference between essential and removable. Essential discontinuities have vertical asymptotes, where removable discontinuity looks like a hole. Let's continue on to number 10. In number 10, there's no way to simplify, so this one's going to either be +infinity or -infinity. Now I'll go ahead and write this negative within my numerator. So if my numerator is negative, I need to see, coming from the left, is my denominator positive or negative? I know that it's approaching 0 because -3 plus 3 is 0, but I'm going to see what sign the values have as they're approaching, and again, that's from the left. So from the left of -3, that's going to be x less than -3. So let's try -4. -4 plus 3 is going to give me a negative number, a -1 to be precise. So because we have a negative over a negative, the sign associated with infinity is going to be positive. So +infinity is my solution in number 10. Now on to number 11. For number 11, we have the limit of 2 times the secant of 2x as x approaches pi over 4, and that's from the right. To start off, I'm going to rewrite this limit. As opposed to having 2 times the secant of 2x, I'm going to write the secant as a fraction, which is 1 over the cosine. So now I'll have 2 times 1 over the cosine of 2x. So that's going to be 2 over the cosine of 2x. And I'm finding the limit of that as x approaches pi over 4 from the left. Now to help me out, I'm going to draw a unit circle. So here's my rough unit circle. Over here, we're at 0 in radians. Over here, we're at pi in terms of radians. And we're approaching pi over 4 from the left. However, if we're looking at our equation, this x is continually being multiplied by 2. So what I'm going to do, just to make this easier to understand visually, I'm going to multiply pi over 4 by 2. So 2 times pi over 4 is going to be pi over 2. So we're approaching this point of pi over 2. And if we're finding the cosine of that as we're approaching from the left, so as we're approaching from smaller numbers, we know that one smaller number is 0. So if we were to plug in 0 for x, that would be 2 times 0, and the cosine of 0 is a positive 1. So we can see that our numerator is always positive, and our denominator is getting closer and closer to 0 because the cosine of pi over 2 is equal to 0. Remember, cosine is represented by the x values, sine represents those y values. So as we're approaching pi over 2, for cosine, that's getting closer and closer to 0. But we're approaching that, as I said, from the positive, and a positive over a positive will be a positive. So positive infinity is our solution in number 11. And again, that's because our denominator was approaching 0 while our numerator approached a number much larger than 0. Therefore, overall, they were approaching infinity. We just had to figure out whether it was a positive infinity or a negative infinity. Now let's move on to number 12. For number 12, we're going to be doing the same thing. I'm going to rewrite this so that we have it in a fraction form. So 2 times the tangent of 2x, I can rewrite the tangent of 2x as sine over cosine. So I'm going to have 2 times the sine of 2 times x all over the cosine of 2x. So as we're approaching 3 pi over 4 in the x, that x value is continually getting multiplied by 2. So if we were to multiply by 3 pi over 4, that would be 6 pi over 4, which simplifies down to 3 pi over 2, if I divide both the numerator and denominator by 2, which is this point here. Now you can see that as we approach 3 pi over 2 for sine, that's going to be a negative. So 2 times the sine of 2x, as x approaches 3 pi over 4, that's going to be 2 times negative 1, since the sine of 2x is approaching negative 1 as x approaches 3 pi over 4, and that's going to be a negative 2, but the important thing to note is that the numerator is negative. Now for the denominator, as we're approaching 2x, we're getting closer and closer to 0 for the cosine. Because remember, sine is represented by y values, so that was negative 1, but cosine is represented by x values, and that's 0. But we need to figure out, are we coming from positive cosine values or from negative cosine values? If we're approaching 3 pi over 4 from the right, that means our x values are greater than our a. So our x values are going to be greater than 3 pi over 4, and they're going to be greater than 3 pi over 2. And again, this is in the relative vicinity. So I want to enter in a super large number to where we go around and around and around the unit circle again. I would just enter in a number that's slightly larger. So something that's slightly larger than 3 pi over 4 would be pi. So if we entered in pi for x, we would have the cosine of 2 pi. And looking at where 2 pi falls, that's going to be coming from the positive cosine direction. So the cosine is going to be approaching 0 from positive values. And a negative over a positive is a negative, therefore the limit is approaching negative infinity. And again, for these functions that are oscillating, meaning that can continue around the same points when dealing with radians, we're trying to look at from the relative or local position. So if I was using 3 pi over 4 and I was trying to find a value that was, excuse me, I wrote this wrong, this is supposed to be 3 pi over 4. If I was looking for an x value that was greater than 3 pi over 4, I chose pi, because 3 pi over 4 is very close to pi. Now for our critical thinking questions, number 13 says to give an example of a right-sided limit that goes to infinity as x goes to 5. So we just need to make sure we're not accidentally creating a removable discontinuity. We want that limit to go to positive infinity as x goes to 5. So we can start with the limit as x goes to 5. Now we just have to find a function where, as x goes to 5, that limit is positive infinity, which means we need a positive number in the numerator, and because we're coming from the right, because it's a right-sided limit, we want that to be approaching 0 from positive values. So let's write 1 in the numerator because that's going to be positive. So now that we have positive in the numerator, we need positive in the denominator. So as x goes to 5 from the right, if we were to subtract 5 from x, as it approached 5 from the right, that would be from values where x is greater than 5, and 6 minus 5 is definitely positive. That's a positive 1. So if we were to write 1 over x minus 5, that's a positive over a positive, so that limit would go to infinity because the denominator is approaching 0 as x approaches 5. So one example is the limit of 1 over x minus 5 as x approaches 5 from the right. Come up with another example and double check it on a graph. Let me know what you got in the comments below. Now for number 14, we're to give an example of a left-sided limit that goes to infinity as x goes to 5. So now we're doing the limit as x approaches 5, and this is from the left. Now when we dealt with our right-sided limit, we just had 1 over x minus 5. However, if we do this approaching from the left, that's going to be a positive over a negative, because this is approaching 0 from the left, so picking a number from the left, let's choose 4. 4 minus 5 is equal to a negative 1. And there's one way to fix this. Let's make the numerator negative. So making the numerator negative, now as opposed to having a positive in the numerator, we have a negative in the numerator, and a negative over a negative is a positive. So this limit is indeed positive infinity. So the limit of the opposite of 1 over x minus 5 as x approaches 5 from the left, or you can read this as limit of negative 1 over x minus 5 as x approaches 5 from the left. And with that, we wrap up our worksheet. If you haven't already, don't forget to like this video, subscribe to my channel, and share this with your peers. For more information, go to maemap.com, maemap.com, and on that website I'll have lesson tutorials and worksheets that you can access.